Use Apache Spark in Azure Databricks. Azure Databricks is built on Apache Spark and enables data engineers and analysts to run Spark jobs to transform, analyze and visualize data at scale. Learning objectives. In this module, you'll learn how to describe key elements of the Apache Spark architecture, create and configure a Spark cluster, describe use cases for Spark. Use Spark to process and analyze data stored in files. Use Spark to visualize data. Prerequisites. Introduction. Azure Databricks offers a highly scalable platform for data analytics and processing using Apache Spark. Spark is a flexible platform that supports many different programming languages and APIs. Most data processing and analytics tasks can be accomplished using the DataFrame API, which is what we'll focus on in this module. In this module, you'll learn how to describe key elements of the Apache Spark architecture, create and configure a Spark cluster, describe use cases for Spark, use Spark to process and analyze data stored in files, use Spark to visualize data. Next unit, get to know Spark. Continue. Having an issue? Get to know Spark. Completed 100 XP. 4 minutes. To gain a better understanding of how to process and analyze data with Apache Spark in Azure Databricks, it's important to understand the underlying architecture. High-level overview. From a high level, the Azure Databricks service launches and manages Apache Spark clusters within your Azure subscription. Apache Spark clusters are groups of computers that are treated as a single computer and handle the execution of commands issued from notebooks. Clusters enable processing of data to be parallelized across many computers to improve scale and performance. They consist of a Spark driver and worker nodes. The driver node sends work to the worker nodes and instructs them to pull data from a specified data source. In Databricks, the notebook interface is typically the driver program. This driver program contains the main loop for the program and creates distributed datasets on the cluster, then applies operations to those datasets. Driver programs access Apache Spark through a Spark session object regardless of deployment location. Microsoft Azure manages the cluster, and auto-scales it as needed based on your usage and the setting used when configuring the cluster. Auto-termination can also be enabled, which allows Azure to terminate the cluster after a specified number of minutes of inactivity. Spark jobs in detail. Work submitted to the cluster is split into as many independent jobs as needed. This is how work is distributed across the cluster's nodes. Jobs are further subdivided into tasks. The input to a job is partitioned into one or more partitions. These partitions are the unit of work for each slot. In between tasks, partitions may need to be reorganized and shared over the network. The secret to Spark's high performance is parallelism. Scaling vertically, by adding resources to a single computer, is limited to a finite amount of RAM, threads and CPU speeds, but clusters scale horizontally, adding new nodes to the cluster as needed. Spark parallelizes jobs at 2 levels. The first level of parallelization is the executor, a Java virtual machine, JVM, running on a worker node, typically, 1 instance per node. The second level of parallelization is the slot, the number of which is determined by the number of cores and CPUs of each node. Each executor has multiple slots to which parallelized tasks can be assigned. The JVM is naturally multi-threaded, but a single JVM, such as the one coordinating the work on the driver, has a finite upper limit. By splitting the work into tasks, the driver can assign units of work to slots in the executors on worker nodes for parallel execution. Additionally, the driver determines how to partition the data so that it can be distributed for parallel processing. So, the driver assigns a partition of data to each task so that each task knows which piece of data it is to process. Once started, each task will fetch the partition of data assigned to it. Jobs and stages. Depending on the work being performed, multiple parallelized jobs may be required. Each job is broken down into stages. A useful analogy is to imagine that the job is to build a house. The first stage would be to lay the foundation. The second stage would be to erect the walls. The third stage would be to add the roof. Attempting to do any of these steps out of order just doesn't make sense, and may in fact be impossible. Similarly, Spark breaks each job into stages to ensure everything is done in the right order. Next unit, create a Spark cluster. Continue. For issues related to this module, create a Spark cluster. Completed 100 XP. 3 minutes. You can create one or more clusters in your Azure Databricks workspace by using the Azure Databricks portal. When creating the cluster, you can specify configuration settings, including a name for the cluster, a cluster mode, which can be standard, suitable for single-user workloads that require multiple worker nodes, high concurrency, suitable for workloads where multiple users will be using the cluster concurrently. Single node, suitable for small workloads or testing, where only a single worker node is required. The version of the Databricks runtime to be used in the cluster, which dictates the version of Spark and individual components such as Python, Scala, and others that get installed. The type of virtual machine, VM, used for the worker nodes in the cluster. The minimum and maximum number of worker nodes in the cluster. The type of VM used for the driver node in the cluster. Whether the cluster supports autoscaling to dynamically resize the cluster. How long the cluster can remain idle before being shut down automatically. How Azure manages cluster resources. When you create an Azure Databricks workspace, a Databricks appliance is deployed as an Azure resource in your subscription. When you create a cluster in the workspace, you specify the types and sizes of the virtual machines, VMs, to use for both the driver and worker nodes, and some other configuration options, but Azure Databricks manages all other aspects of the cluster. The Databricks appliance is deployed into Azure as a managed resource group within your subscription. This resource group contains the driver and worker VMs for your clusters, along with other required resources, including a virtual network, a security group, and a storage account. All metadata for your cluster, such as scheduled jobs, is stored in an Azure database with geo-replication for fault tolerance. Internally, Azure Kubernetes Service, AKS, is used to run the Azure Databricks control plane and data planes via containers running on the latest generation of Azure hardware, DV3 VMs, with NVMe SSDs capable of blazing 100s latency on high-performance Azure virtual machines with accelerated networking. Azure Databricks utilizes these features of Azure to further improve Spark performance. After the services within your managed resource group are ready, you can manage the Databricks cluster through the Azure Databricks UI and through features such as auto-scaling and auto-termination. Note: you also have the option of attaching your cluster to a pool of idle nodes to reduce cluster startup time. For more information, see pools in the Azure Databricks documentation. Next unit, use Spark in notebooks. Continue. For issues related to this module, use Spark in notebooks. Completed 100 XP. 6 minutes. You can run many different kinds of application on Spark, including code in Python or Scala scripts, Java code compiled as a Java archive, JAR, and others. Spark is commonly used in two kinds of workload: batch or stream processing jobs to ingest, clean, and transform data, often running as part of an automated pipeline. Interactive analytics sessions to explore, analyze, and visualize data. Running Spark code in notebooks. Azure Databricks includes an integrated notebook interface for working with Spark. Notebooks provide an intuitive way to combine code with markdown notes, commonly used by data scientists and data analysts. The look and feel of the integrated notebook experience within Azure Databricks is similar to that of Jupyter Notebooks, a popular open-source notebook platform. Notebooks consist of one or more cells, each containing either code or markdown. Code cells in notebooks have some features that can help you be more productive, including syntax highlighting and error support, code auto-completion, interactive data visualizations, the ability to export results. Tip: to learn more about working with notebooks in Azure Databricks, see the Notebooks article in the Azure Databricks documentation. Next unit, use Spark to work with data files. Continue. For issues related to this module, explore existing questions using the hashtag Azure Training tag or ask a question on Microsoft Q&A. For issues related to certifications and exams, visit our credentials help. Use Spark to work with data files. Completed 100 XP. 5 minutes. One of the benefits of using Spark is that you can write and run code in various programming languages, enabling you to use the programming skills you already have and to use the most appropriate language for a given task. The default language in a new Azure Databricks Spark notebook is PySpark, a Spark-optimized version of Python, which is commonly used by data scientists and analysts due to its strong support for data manipulation and visualization. Additionally, you can use languages such as Scala, a Java-derived language that can be used interactively, and SQL, a variant of the commonly used SQL language included in the Spark SQL library to work with relational data structures. Software engineers can also create compiled solutions that run on Spark using frameworks such as Java. Exploring data with data frames. Natively, Spark uses a data structure called a Resilient Distributed Dataset, RDD, but while you can write code that works directly with RDDs, the most commonly used data structure for working with structured data in Spark is the data frame, which is provided as part of the Spark SQL library. Data frames in Spark are similar to those in the ubiquitous Pandas Python library, but optimized to work in Spark's distributed processing environment. Note: in addition to the DataFrame API, Spark SQL provides a strongly typed dataset API that is supported in Java and Scala. We'll focus on the DataFrame API in this module. Loading data into a dataframe. Let's explore a hypothetical example to see how you can use a dataframe to work with data. Suppose you have the following data in a comma-delimited text file named products.csv in the data folder in your Databricks file system, dbfs, storage. CSV copy. Product ID, product name, category, list price 771, mountain 100 silver, 38, mountain bikes, 3,399.9900 772, mountain 100 silver, 42, mountain bikes, 3,399.9900 773, mountain 100 silver, 44, mountain bikes, 3,399.9900. In a Spark notebook, you could use the following PySpark code to load the data into a data frame and display the first 10 rows. Python copy. %PySpark df equals spark.read.load/data/products.csv, format equals CSV, header equals true, display df.limit 10. The %PySpark line at the beginning is called a magic, and tells Spark that the language used in this cell is PySpark. Here's the equivalent Scala code for the products data example. Scala copy. %Spark val df equals spark.read.format CSV. Option header, true. Load/data/products.csv, display df.limit 10. The magic %Spark is used to specify Scala. Tip: you can also select the language you want to use for each cell in the notebook interface. Both of the examples shown previously would produce output like this. Expand table. Product ID, product name, category, list price. Specifying a dataframe schema. In the previous example, the first row of the CSV file contained the column names, and Spark was able to infer the data type of each column from the data it contains. You can also specify an explicit schema for the data, which is useful when the column names aren't included in the data file, like this CSV example. CSV copy. 771, mountain 100 silver, 38, mountain bikes, 3,399.9900 772, mountain 100 silver, 42, mountain bikes, 3,399.9900. Filtering and grouping data frames. You can use the methods of the dataframe class to filter using SQL expressions in Spark. The dataframe API is part of a Spark library named Spark SQL, which enables data analysts to use SQL expressions to query and manipulate data. Creating database objects in the Spark catalog. The Spark catalog is a metastore for relational data objects such as views and tables. The Spark runtime can use the catalog to seamlessly integrate code written in any Spark-supported language with SQL expressions that may be more natural to some data analysts or developers. One of the simplest ways to make data in a dataframe available for querying in the Spark catalog is to create a temporary view, as shown in the following code example. Python copy. df.create or replace temp view products. A view is temporary, meaning that it's automatically deleted at the end of the current session. You can also create tables that are persisted in the catalog to define a database that can be queried using Spark SQL. Note: we won't explore Spark catalog tables in depth in this module, but it's worth taking the time to highlight a few key points. You can create an empty table by using the spark.catalog.create table method. Tables are metadata structures that store their underlying data in the storage location associated with the catalog. Deleting a table also deletes its underlying data. You can save a data frame as a table by using its SaveAsTable method. You can create an external table by using the spark.catalog.createExternalTable method. External tables define metadata in the catalog but get their underlying data from an external storage location, typically a folder in a data lake. Deleting an external table does not delete the underlying data. Using the Spark SQL API to query data. You can use the Spark SQL API and code written in any language to query data in the catalog. For example, the following PySpark code uses a SQL query to return data from the products view as a data frame. Python copy. Bikes_df equals visualize data. Completed 100 XP. 6 minutes. One of the most intuitive ways to analyze the results of data queries is to visualize them as charts. Notebooks in Azure Databricks provide charting capabilities in the user interface, and when that functionality doesn't provide what you need, you can use one of the many Python graphics libraries to create and display data visualizations in the notebook. Using built-in notebook charts. When you display a data frame or run a SQL query in a Spark notebook in Azure Databricks, the results are displayed under the code cell. By default, results are rendered as a table, but you can also view the results as a visualization and customize how the chart displays the data, as shown here. The built-in visualization functionality in notebooks is useful when you want to quickly summarize the data visually, when you want to have more control over how the data is formatted, or to display values that you have already aggregated in a query. You should consider using a graphics package to create your own visualizations. Using graphics packages in code. There are many graphics packages that you can use to create data visualizations in code. In particular, Python supports a large selection of packages, most of them built on the base matplotlib library. The output from a graphics library can be rendered in a notebook, making it easy to combine code to ingest and manipulate data with inline data visualizations and markdown cells to provide commentary. For example, you could use the following PySpark code to aggregate data from the hypothetical products data explored previously in this module, and use matplotlib to create a chart from the aggregated data. Python copy. From matplotlib import piplib. The matplotlib library requires data to be in a pandas dataframe rather than a Spark dataframe, so that a pandas method is used to convert it. The code then creates a figure with a specified size and plots a bar chart with some custom property configuration before showing the resulting plot. The chart produced by the code would look similar to the following image. You can use the matplotlib library to create many kinds of chart, or if preferred, you can use other libraries such as Seaborn to create highly customized charts. Note: the matplotlib and Seaborn libraries may already be installed on Databricks clusters, depending on the Databricks runtime for the cluster. If not, or if you want to use a different library that is not already installed, you can add it to the cluster. See cluster libraries in the Azure Databricks documentation for details. Next unit, exercise.